Hello and welcome to our OES application lab in Germany. Today we are so proud to announce the latest addition to our OES product line, the Q4 POLO, or as we call it, the Little Giant. So as you can see here, the Q4 POLO is a very compact benchtop OES spectrometer with approximately 50 centimeters by 50 centimeters footprint, and I have two versions of it today with me in the lab. This version that you see sitting next to me is the one with the smart tray. So you can use the smart tray to place your analyzer laptop on it, so you can have both your analyzing instrument and the analyzing computer together within such a small footprint. Or alternatively, you can use the smart tray to place your production samples or your certified reference materials or your setup samples for recalibration for your convenience. So today together we will analyze some samples and take a closer look at the outstanding performance of the Q4 POLO. But before that, I would like to start with the basics of the OES for those people who may not be so familiar with the technique. So what is OES? OES stands for Optical Emission Spectrometry, which is the go-to analysis technique when it comes to analysis of metals. So we use this technique to precisely analyze the chemical composition of metals such as titanium or ferrous alloys, copper alloys, aluminum alloys, and many more. And an OES spectrometer like the Q4 POLO will let us make the analysis and get the chemical composition information of all those bases and many more. By the way, when I see base or matrix, I'm referring to the element which makes up most of the sample. So if we're talking about iron matrix, we are talking about ferrous alloys. If it's copper, we are talking about copper alloys like bronze and brass and so on. So how does the OES technique works? Let me explain it to you briefly. Inside here, below the spark stand plate, we have what we call the lower electrode. When we put the sample on the spark stand plate and start the analysis, the instrument starts sparking the sample surface with small sparks at a high frequency. So that sparking creates a small plasma inside the gap between the tip of the electrode and the sample surface. And this plasma emits light at different wavelengths. So we collect that light and send it to the state-of-the-art CCD detectors that we have inside the instrument to analyze the wavelengths, which, by the way, gives us the information about the elements that we have inside the metal sample. And we also detect the intensity of each of those lines or wavelengths, which gives us the information about the chemical concentration of each of those elements in the sample. And this is how the technique works. But if you ask me, why do we even need to make this kind of analysis on metals? Actually, the answer is pretty simple. We need to make this analysis to get the chemical composition of the metal, because it is so important to know precisely the chemical composition of each metal, because it directly affects physical and chemical properties of metals. So each metal manufacturer needs to make sure that the product that they make is within the specs specified with the grade. And when I say grade, and I'm referring to a specific chemical composition for that specific alloy. Okay, so in the ferrous world, for example, there are thousands of different alloys and grades for iron, and same applies to copper and nickel and aluminum and the others too. So manufacturers need to analyze their material and make sure that the chemical composition is within the specs specified by the norms. And after that, we can go to the next topic, which will be the sample prep. Now that we know what the OES is and how it analyzes a sample, the next step before analyzing the actual sample is to prepare the sample. As you can see here, this metal sample was ground with an aluminum oxide sandpaper. So when we want to prepare hard materials like titanium or ferrous alloys, etc., we generally use this sandpaper. And when we want to analyze softer materials like aluminum, lead, or tin, and the right method to prepare the sample is to machine the sample surface. But in both cases, we should be careful and we try to have a really flat surface because it really affects the precision on the analysis. And we should also pay attention to that the sample surface should be free of contamination. So after grinding or machining, we should make sure that nobody touches and we don't contaminate the sample surface so that we can get some repeatable results. Okay, so let's go ahead and analyze some samples. I want to start with this cast iron sample. So to do that, I go to my instrument and lift up my clamp and twist it so I can lock it in its place. I remove this sample and I place my cast iron sample on the spark stand plate here, and then I take the clamp and put it back on the sample. The moment the upper electrode touches the sample surface, you can see that this green light turns on, which means that the instrument is ready to analyze. So what I'm going to do next is to go to my computer, enter the sample information, and then start the analysis. First thing I do on the Elemental Suite is to choose the right method, which is FE120 for cast iron, and then I click on Sample to enter the sample ID. In this case, it is ductile cast iron, and then I simply press Save and Close. What I do next is to press the button with the green light around it on the instrument to start the analysis. As you can see, analysis has just started and the timer is running. And also on the lower right hand side of the screen, you can see a set of sequences that the instrument goes through during a complete analysis. So cast iron is an iron carbon alloy with a typical carbon content varying from roughly 2% to 4%. This iron alloy has been widely used by humanity for thousands of years already to make various items such as plowshares, pots, cannons, bridges, and many more. Among the cast iron types are the gray cast iron, white cast iron, malleable cast iron, and ductile or nodular cast iron like the one we are analyzing now. Ductile cast iron is also called nodular cast iron because carbon forms graphite in the form of small nodules, which makes the quantitative carbon analysis more difficult as the carbon distribution in the material is not homogeneous. But as you can already see on the analysis screen, this is not an issue for the Q4 POLO at all, and it can precisely analyze the carbon together with other main alloying elements such as silicon, manganese, nickel, magnesium, chromium, and phosphorus in cast iron. All right, we have just finished analyzing the cast iron sample. Let me take the sample and show you what it looks like. So you can see the burn marks on the surface of the sample. These are the areas that we spark at high frequency to get the chemical information. Okay, so the next sample that I would like to analyze is non-alloy steel. And again, I take my sample, I go to my instrument, I clean the tip of the electrode with my metal brush, and then I place my sample on the spark stand plate and then put the clamp on it. Then again, I go to my software, Elemental Suite, to enter sample information and then start the analysis. I'm on the Elemental Suite again. This time I press Reject Analysis to delete the results from the previous measurement, and again I choose the right method, which is FE110 for low alloy steel. I change the sample ID, I delete the previous one and write non-alloy steel, And instead of pressing save and close, this time I press the right arrow button, which takes me to the material screen where I choose the grade information. And then I activate the low alarm and high alarm for this grade, which will bring up the limits specified for this grade. And then I start the analysis, and the counter has just started running. So non-alloy steel, in terms of chemical composition, is very similar to low alloy steel. The main difference between the two is the fact that no other elements are added during the smelting process, which is basically the extraction of a metal from its ore. Unlike alloy steel, during whose production some other elements like chromium and cobalt are added, the non-alloy steel does not have these additional elements and therefore has less durability. To overcome this, the non-alloy steel goes through a heat treatment called tempering. Non-alloy and low alloy steels usually have from 1% to 5% of alloying elements. In low alloys, other elements can be added to improve the material's physical properties. For example, while chromium addition improves the corrosion resistance and hardness, nickel adds toughness, and molybdenum improves the material strength. Low alloy steels have a wide variety of application areas and are usually used for manufacturing of construction equipment, pipes, ships, automotive, and in powder form, it's also used in additive manufacturing. And now I can also change the grid layout on my screen. And with the slider on the right hand side, I can also make the font either smaller or bigger. And if I press the same button again, and I can toggle the grid layout to the previous version. Okay, the analysis is now completed. Let's take our sample and let's have a look at it. So, as you have seen on the Elemental Suite software already, the Q4 POLO has done an excellent job on both non-alloy steel and cast iron samples so far. But what I would like to do next is to get a 316L stainless steel. This is a very common alloy in the steel world, and analyze this one. Okay, and again I go to my instrument, I brush the tip of my electrode, I place my sample, I lower the clamp, and then, as always, I go back to my computer, to my Elemental Suite, to enter the sample information. I'm back on Elemental Suite, so I click on Reject Analysis, and then I choose FE130 Stainless Steel Method, and I change my sample ID to 316L. And this time, instead of choosing the grade, I prefer to perform a PMI and find the matching grade. And after entering all the information, I just press the start button and start the analysis. So stainless steel is one of the most common steel alloy used today due to its high corrosion and heat resistance. There are more than 100 stainless steel grades, and most of them can be categorized under 5 main groups: austenitic, ferritic, martensitic, duplex, and precipitation hardening stainless steel. The sample we are analyzing now is grade 1.4404 or 316L stainless steel, which falls into the austenitic stainless steel category. The austenitic stainless steel is by far the most common stainless group, and it can be further divided into 2 subgroups: 200 series and 300 series. 200 series has a higher manganese and nitrogen content and a lower nickel concentration. While this leads to an improvement in yield strength, it also weakens the corrosion resistance. 300 series, on the other hand, has better corrosion resistance. The best known grade in the 300 series is 304, which has around 18% chromium and from 8% to 10% nickel. Type 316 is probably the most common austenitic stainless steel. It has approximately 2% molybdenum in it, and this gives it a better corrosion resistance than type 304. Now that the analysis has been completed, I simply press the PMI button to do a positive material identification. And now Elemental Suite is looking for the matching grades in the total material database. And the first matching grade is 1.4401, which has minimum 10.5% of nickel. And at the end of our analysis, we got 10.23. That's why it's highlighted in red. And the next matching grade is 1.4404, which is exactly the same grade that we analyzed together. So I press Leave Workflow to go back to my analysis screen. Okay, now the stainless steel analysis is complete. On the Elemental Suite, we saw that we could identify the grade. And again, the Q4 POLO did an excellent job on identifying the grade and doing the chemical analysis. So again, let's have a look at the sample. As you can see here, we have very nice burnt marks. So, and around each spot that we sparked, we see a black circle. And this is what we would like to see after a good analysis. If for some reason you don't have the black circle around the spark spot, it might be a good indicator to a gas quality issue. So you may want to check the quality of your argon gas, and you can also check the pressure of that tank. Okay, now we will continue with the aluminum sample. This is also prepared pretty nicely. As you can see, the surface is machined and pretty flat. Normally when we switch between different matrices, like we do here from ferrous base to aluminum base, from aluminum to copper, we usually change the electrode and use a dedicated electrode and a metal brush for each base just to avoid cross-contamination. But for the sake of this demonstration, I'm not going to do that. I'm just go ahead and brush out the tip of the electrode and place my aluminum sample on the spark stand plate and lower the clamp. And then again, I go back to Elemental Suite. First thing I do is to remove the previous analysis, and then I go to Aluminum tab and choose Aluminum 101, the Master Alloy method. And then I change my sample ID to SS384, which is the name of this particular sample, and then I choose 384 grade. And I press Save and Close. And after that, as always, I press the button on the instrument to start the analysis. As you may have already noticed in the grade limits on the screen, the main alloying elements for the specific grade are silicon, copper, and iron. In addition to these, zinc, magnesium, and manganese are also important alloying elements for aluminum alloys in general. 1000 series aluminum alloys, also known as commercially pure aluminum, have high corrosion resistance and conductivity. It is generally used for food packing and electrical applications. 2000 series aluminum has copper as the main alloying element, and it is usually used in the aircraft industry. 3000 series has both manganese and magnesium, and it is a general purpose aluminum alloy typically used in beverage cans and heat exchangers. 4000 series is an aluminum silicon alloy, which is generally used as filler material. 5000 series, due to magnesium addition, has high strength and corrosion resistance. It is used in construction and marine applications. 6000 series is an aluminum magnesium silicon alloy with excellent corrosion resistance and is widely used in automobile production. And finally, the 7000 series has a very high tensile strength due to zinc, magnesium, and copper. This alloy is very common in aircraft and aerospace industries. All right, so this high silicon aluminum sample was the last one that we analyzed today. And in the Elemental Suite, we saw that Q4 POLO did a very highly precise, accurate analysis on this aluminum sample. We also saw that the results we got at the end of the analysis actually matched pretty well what is specified by the grade. So again, let's take our sample and have a look at the sample surface. We have pretty well burn spots on the sample surface with black circles around them. So the Q4 POLO is the excellent benchtop OES spectrometer for ferrous and non-ferrous applications. It's either cast iron, stainless steel, or low alloy, or aluminum, or copper, or any other application. The Q4 POLO is the right solution for foundries and many other metal producers. If you have any questions about the Q4 POLO, you can always get in touch with us by using our website, bruker.com. We will be more than happy to help you and provide you with information you might need. So with that information, I think we come to the end of this presentation today. I want to thank you all for joining us today. And until next time, goodbye.